Thanks.
Thank you.
Okay, so hi everyone. Today's pizza seminar is provided by Mark Gieles, who obtained his PhD in 2006 from the Utrecht University. Then he moved to ISO in Chile in 2006, yes. And then in 2009, he moved to Cambridge as a Royal Society University Research Fellow. Finally, he moved to Surrey in 2013, and from 2018, he is an ICREA professor at ICCUB. He works, his research focus, well, we will know in a while, but his research focuses on trying to understand the formation and dynamical evolution of star clusters to shed light on stellar initial mass function, black holes, gravitational waves, and the population of globular clusters. Today he's talking to us about formation of globular clusters with extremely massive stars. The floor is yours.
All right, thank you very much. Thank you very much for the invitation. I've had a fun discussion already with...
Okay, I say okay.
Sorry?
If you click on OK, it's down. It's the meeting is being recorded again.
Yeah, yes. Okay. It's been fun chatting to Mar about AGN so far. Actually, also this talk is going to be a little bit outside of my own comfort zone. So everything we just heard about what I do, I'm not really talking about that. It's a bit of an idea inspired very much by an observational problem that's been long-standing and also very recent exciting new observations from high redshift. So if the word globular cluster doesn't immediately get you very excited, or if hypothetical stars above 1,000 solar masses don't really get you interested, perhaps you care more about is this working? No. Some JWST observations, in particular nitrogen-loud galaxies. I'll touch on that a little bit. If that really doesn't get you very excited yet, I will try to connect a little bit to galaxy formation. And that's also outside of your scope. Maybe you like black holes. So I'll also talk about that a little bit. So let me first introduce the problem that has been on my mind for nearly a decade now. And it's illustrated by this figure. I think the color scheme is just by chance illustrating the problem. It's not actually illustrating the problem. But here you see two globular clusters in the Milky Way, M3 and M13. Very similar in age, very similar in mass, very similar in how they look like, and very similar in metallicity. But if you look very carefully, you see a tiny little bit more blue stars here. I think that's really just not true, but you see it, but it's not really real. What is real is if you look at the CMD of these two clusters, is that there are actually a few more blue stars here on the horizontal branch, right? So the extent of the horizontal branch in M13 is just a little bit more to the UV than in M3. And this is odd, and it's been noticed for other clusters as well, that why at the same metallicity do they have these different stellar evolution properties? And that's been dubbed the second parameter problem. So apart from metallicity, there must be something else going on here. And this is known since the 60s. Now, since HST, we know there's other things that are strange about globular clusters. So if you look at the main sequence, which for a single age stellar population, you expect to be a very, very narrow distribution if you have very good photometry, actually there's a broadening. And there's a known broadening to the red due to binary stars. But the intriguing problem here is that we have a broadening towards the blue. And the working hypothesis is that this is because some stars are slightly enriched in helium. And if you have higher helium abundance, you also can explain the extreme horizontal branch morphology. Now, apart from the photometry, also spectroscopy from the ground has led to some really strange abundance patterns at the light elements. So nitrogen, oxygen, but also sodium, magnesium, aluminium. I show here a compilation of the Caretta Flames survey that surveyed about 20 globular clusters. And if you plot these two particular light elements in a diagram, you see that they're not single abundance patterns at all. There's a clear spread, and there's a well described anticorrelation. There's another anticorrelation that shows up in some globular clusters, which is magnesium against aluminium. And that's quite rare, actually, and I'll explain a bit more where and when you see it, but hopefully also why you see it. Now, these anticorrelations are not random spreads in elements. They are well-known outcomes of hydrogen burning at high temperatures. So the classic one we've all probably seen in our undergraduate courses, except for maybe the engineers in the room, but the astronomers in the room, is that if you burn hydrogen in the CNO cycle, you have all these steps and reaction chains. Some are slow and some are fast. And the slow reaction chains will lead to a pileup at certain abundances, right? So in this case, you have a pileup of nitrogen and you have a depletion of carbon, just because the reaction chains away from carbon are faster than towards nitrogen. Forget about all the complexities here, but the same thing, the idea is that the same thing happens with oxygen and nitrogen and sodium, sorry, in the neon-sodium chain, and with magnesium-aluminium in the magnesium-aluminium chain. So you can say, okay, fine, well, there you have your explanation for the anticorrelation. The problem is that these temperatures are well above the temperatures of the stars in globular clusters, right? So the typical star in the globular cluster is like the sun, where if you measure the temperature in the center, you find it's above 15 million Kelvin, barely igniting the CNO cycle. So why do we see the outcome, or the ashes, as the nuclear physicists call it, of these cycles at temperatures well above the temperatures of these stars? Now, there's some differences between these observational properties. So if you look at the shape of these anticorrelations, so these are two clusters with different masses, about a factor of 10 different, you can see that the slope is slightly different, and it's a flatter correlation or flatter slope in these more massive clusters. And that is what you expect temperature to do, right? So this suggests that you've processed sodium at or hydrogen at higher temperatures in this cluster compared to that cluster, right? So then the spread is the result of, you have some extreme elements coming out of hydrogen burning at high temperatures. Somehow it mixes with normal material, and then stars, they get different fractions of this polluted material in their abundances. For magnesium and aluminium, these are now individual dots are individual globular clusters. If you plot the extent of this anticorrelation, so basically how wide is it, what is the spread along the anticorrelation, you can see that it is higher for clusters that are more massive. It's a similar idea as here. The extent would be also a temperature indication, and it's also anticorrelated with iron abundance, right? So the iron abundance is approximately the same for all the stars. So it's sort of a pristine condition of the gas of which the globular cluster was made. And it appears to have an effect on the extent of this anticorrelation. So if you would parameterize this and use positive indices, there's some sort of power law correlation that you can fit here, where the temperature that you infer from the properties of the abundances seems to go up with cluster mass and down with metallicity. So I'm trying to be completely agnostic here still about where this temperature could be found, right? So since about the 80s or 90s, people have been trying to understand, like, what could be a polluter, right? So a source that can reach those temperatures and can then share the material that it's creating with the globular cluster stars that then form. So classic there are two main channels, and there's many more flavors. So apologize to people who have been involved in any of the varieties that came out of this, but I think it's fair to subdivide the models in two categories. One is AGB stars that undergo very high temperature hydrogen burning in a shell burning phase in the late stages. But these are stars with progenitor masses of 3 to 8 solar masses, or massive stars, generally speaking. But the particular flavor of massive stars people invoked were fast rotating massive stars, such that you can get all this burning material to the surface of the star, because a rotating star mixes, and you can get it out of the star, right? Because one thing is, of course, reaching the temperature, but if you make something in the core of a star and it stays there, you don't solve the problem. You still need to get it out and make new stars, or share it somehow with the other stars. So this is a very incomplete list of papers on this topic, and I won't go into detail. Just want to highlight that there's different flavors of how to get the material from the polluter into the new stars. One more popular scenario is where you do it in generational steps. So you have first some initial population of stars that creates all this gas that's enriched in all these products, and then you make a second generation. But there's also attempts of doing it in one go, where you try to enrich while you're making the first generation of stars, right? So this is a bit more attractive with massive stars because they live very short. And AGB stars, you have to wait about 30 million years before you get all this material, right? And without going into details and without criticizing too many other people, I would say this is the more challenging way of doing it, because you need to somehow get the iron abundance to stay the same for all the stars in the cluster, while getting AGB winds to come out. And that happens after supernova happen. So, people still think that might happen. I am very skeptical that this could work. Now, the key challenges, there's many, but the three I think are the hardest for any model trying to explain this, is that if you look at a population of globular clusters, is that the helium spread that people infer from the main sequence broadening is actually tiny. It's really, really small. And if you wait for a fast rotating massive star to have significant stellar winds with high sodium and aluminium, you can easily be over here, right? Because these stars, they basically burn until they're completely helium. So you need to keep helium very low. Then the fraction of stars in a globular cluster that is polluted by these materials is very high. Like it's more than half of the stars. And there's also an increase if you would count the number of stars per unit of mass, because it's small for low mass clusters and it's higher for higher mass clusters. And there seems to be a temperature dependence of the polluter on both the mass of the cluster and the iron abundance of the cluster. Right, so this is not obvious to do with AGB stars or fast rotating stars, where you could either get a constant fraction, and typically this fraction would be very small. And so people have played with the IMF, making the IMF top heavy, of making a particularly high abundance of AGB stars. It's very hard to get these things to work. So then we got light from JWST, and this problem, I think, got some fresh energy, because we started seeing some very similar abundances at a redshift of 11 to the globular clusters, right? So this is a well-known galaxy at GNZ11 at a redshift of 11, where people could take spectra and determine abundances, not of sodium and aluminium, but of nitrogen. So I show here one result of the nitrogen over oxygen versus oxygen, and it's up here. And the error bar is, of course, quite large, and these are local galaxies. So this is way off and very different from what we see in nearby star-forming galaxies. So then my collaborator, Corinne Charbonnel, who has been thinking about much more massive stars than the ordinary, so supermassive stars in the 10 to the 4 solar mass range. And first he showed that this abundance of the GNZ11 galaxy is actually really similar to the sort of strange abundances in globular clusters, right? So these dots here are, these three branches are the anticorrelations in these units. So this is due to the carbon-nitrogen anticorrelation, but plotted in the same abundances as we have from JWST. And you can see that for 47 TAC, you actually see that the extreme stars in 47 TAC are very close to GNZ11. Right, so and then she said, okay, now we can make a model of a star of 10 to the 4 solar masses. And this is what you get out of this star. And if you then dilute it with normal mass, you expect stars to be along this line, and sort of kind of goes to the data points. Like, hooray, supermassive stars, right? So she wrote a paper, and not even a week later, Jorik Fink came along and said, oh, actually, you can also do it with 300 solar mass stars. You really don't need 10 to the 4 solar masses. And then other people came by and said, well, we might be seeing a black hole here, right? And then the same people came by and say, well, we might be seeing another type of black hole, or POP3 stars, or AGB stars. So everybody can explain a high nitrogen abundance, right? That's clearly not a problem. But it is intriguing that in the mass range above 100 solar masses, you have this high nitrogen abundance kind of for free. And so that's very easy. And above 100 solar masses, you also get it on the surface, right? So every star above 2 solar masses would burn through the CNO cycle and have a high nitrogen abundance, but in the center. Above 100 solar masses, either by convection or a little bit of rotation, this material gets to the surface. right? So stars above 100 solar masses are very attractive, but which category? That's not clear at all, because these stars are to some extent very similar, right? Their mass to light ratio is constant. They live for about 2 or 3 million years, and their nitrogen over oxygen are very, very similar. So it's very difficult to say from just nitrogen which one we need, but we were going to try and see, can we in this category find a favorite polluter and also make it, right? So not just get the yields, not just get the chemistry, but also how do you form these stars, and are there any testable predictions we can come up with to go after. So here to illustrate that these very massive stars are in the 100 to 1,000 are actually not unicorns, right? They exist. We have seen them. The nearest example is in the star-forming region Turgidorades in the LMC, where a very dense cluster of about 10 to the 5 or a few times 10 to the 4 solar masses has stars in the center here, which the individual stars have estimated masses of 200 solar masses. Now, if you correct for wind mass loss and some evolution, these initial masses might be up to 300 solar masses. And what is interesting is that if you, this is work by Paul Crowther, if you combine the spectra of these individual stars and you make spectra of the whole region, you see a line here at 1614 angstrom, which is the helium-2 line. And if you compare to the light of these individual stars just in the center, this entire line, which is seen here in the whole region, the entire line comes from those 5 or 7 stars. Right? So this helium-2 line seems to be a very good indicator of stars above 100 solar masses. And that's a common feature in star-forming galaxies at high redshifts, right? So this helium-2 line, you don't see it in a Milky Way star-forming regions where the stars are maybe 50 solar masses, but when you go to high starburst regions, you start seeing this helium-2 line. And now we are building up statistics, and thanks to JWST, this slide is a little bit pre-JWST, so there's also a lot of data on more local galaxies with Muse and other surveys. But it seems to be, this is a particularly nice paper where they also try to understand, is it really unique to very massive stars, or are there maybe other lower mass Wolf-Rayet stars or binaries that can do it? And they find some equivalent width criteria, and they say above that, it's very hard to do it with anything else than 200 or 300 solar mass stars. And they're ubiquitous in the UV bright galaxies, but really in the top 10% of these galaxies, right? Now, it's not that every galaxy shows it. So it could be a short-lived phase, or it could be an extreme phenomena that you only see in the brightest 10%. So the question we've asked is like, well, what if the IMF is just a continuation, and in some galaxies you just don't reach above 100 solar masses, right? So our galaxy might be just the star formation rate's too low, we just don't populate the IMF. But what if it just continues? So I avoid the term top-heavy IMF, because usually people change the slope when they talk about top-heavy IMF. We say it's salpeter, but we want to know what would happen if you start making these stars, and how would you make those stars? Now, and then this whole project is basically stems from conversations with my next door neighbor at the UB, Paulo, who works on star formation, but at extremely high resolution, and therefore also relatively low star formation rate by sort of numerical constraints, right? He cannot model a galaxy because he forms from the brown dwarf limits up to 100 solar masses. He forms stars almost self-consistent, right? So he does these really high resolution star formation simulations, and he finds that the growth of a massive star is not what you expect in the core collapse model or in the competitive accretion model, but it's something in between. So you have an inflow of filamentary structures that form by turbulence on a larger scale, on a sort of 10 to 100 parsec scale. And these filaments they start crossing at certain higher density regions and feeding seed stars that grow in mass in time. And it's happening relatively slowly, in the sense that it can take a few million years to make a star of 10 solar masses. Right? So these filaments, they accrete onto a disk, and then the disk accretes onto on the star. And one of the most interesting outcomes of this model I found is that the most massive star you can make in a cloud, he's very careful with using the word clouds, because if everything is turbulent, clouds are transient features, right? It's an overdensity that exists for one dynamical time, and then it is gone again. So he calls it well, structures or something. So, but if you have the total mass in some region, then he finds that you can squeeze about 0.1% of that mass into the most massive star. And that means that if you have larger gas masses, you can make more massive star. And he says that should be just linear, right? So that was what got me very excited about trying to work this further out, because it's very natural to think that at higher redshift you can have higher gas masses, right? Actually, it's the gas density that drives it, but it results in the same thing. So just order of magnitudes, right? If you put 0.1% of a cloud into a star, and you say about 10% of all the gas turns out into a cluster, right? So 10% star formation efficiency, that sort of works out for the Milky Way, right? So you make clusters of around 10 to the 4 solar masses, like Western 1 or the Arches or NGC 3603. And the most massive star we know of is about 100 solar masses. If you go up to R136 that we just discussed, it's maybe a factor of a few larger, both in cluster mass, but also in stellar mass. And then what we said, well, if you continue this extrapolation, then a star cluster, which was initially 10 to the 5 or 10 to the 6 solar masses, must then have had stars between 1,000 and 10,000 solar masses, right? Just by star formation, the exact same physics that makes a 10 solar mass star would make a 10,000 solar mass star, but you just do it much faster because the densities are much higher. So, and if you look at the growth of stars in these models, the accretion is actually about constant in time. This is very, very distinct from competitive accretion, where it's bon deheuel. So you expect a sort of runaway growth of a star. But here you see a sort of a steady flow from larger scales at a constant velocity onto this star, and they grow steadily in time, right? At some point, some feedback will stop this in time, but otherwise you see it's nicely linear. And if you plot the final time it takes to make a star of a certain mass, so after accretion has stopped, you see it's on average, it's a bit of a scatter plot, but it's a power law relation. And there's a boundary here on the top, which is essentially the dynamical time of the gas. And there's a maximum accretion time that follows from the gas mass and the dynamical time, and one free parameter, right? So this empirical model we use from the numerical simulations, basically we fit on this little epsilon here to say that's the fastest accretion rate. And then you can parameterize basically star formation and scale it up, right? So you can say this time scale we know, the maximum accretion rate we therefore know after we fit for this little epsilon. And then we just fit a square root relation to the time it takes for a star to form. And it's a very intuitively sane result, right? It takes a bit longer to make a more massive star. Makes sense. And then where these lines cross, that's your most massive star. And if you would have higher gas mass clouds, you can go to the right. And if you have higher gas densities, you would move down, right? So then you can do everything before feedback of supernova stars. And then you can maybe squeeze in 1,000 solar masses in time before supernova stop everything. So those are our ingredients, and then we kind of put in a pot and we stir and we make a little recipe, a very simple toy model, where we say we have two parameters essentially that we can vary to make the mass function of a cluster populations. One is the gas density that sets the accretion rate and the time scale for formation of the cluster. And if you take densities inferred from surveys at redshift of 2 or 3 of gas clouds, about 10 to the 3 solar masses per parsec squared, you find that you have dynamical times of about 1 million years, 2 million years. So you could make the whole cluster before any significant feedback from supernovae. And then we apply this timescale for individual stars, and we do this constant accretion as Paolo sees in these models. And the second ingredient is metallicity, so the pre-star formation metallicity of the gas clouds, right? Because the iron abundance sets the winds of massive stars. So if you have lots of metals, line-driven winds are stronger. And this has been parameterized in literature, and we use this simple fit by these papers. And you can see that if you do this at high masses, this very quickly becomes really important, right? So the wind mass loss rate will at some point win from the accretion rate which we take to be a constant for every star, right? But it also depends on metallicity. So you can see here, this is models where people do use MESA, the stellar evolution code, to model a 500 solar mass star. And you can see that within a million years or so, these stars lose almost all of their mass, even before they start burning hydrogen, right? So it's a great way of getting low helium stuff out of a star, these winds. So then all we do is we combine it. Very simple. Right? We say stars grow in mass according to these relations, but then at some point, the wind masses rate starts to slow down this accretion. And then is when we start getting this nuclear burning products, because nuclear fusion starts here. So if you have a 10 solar mass star, the Kelvin-Helmholtz timescale is very short. And so you basically be on the main sequence, but you're also accreting. Right? So the star grows in mass, but it starts to already ignite the CNO cycle, and everything that comes with it starts to come out through these winds. So then we do this, we model the mass function as a function of time. So this is the IMF above 1 solar mass. We say every star above 1 solar mass evolves like this. So initially, nothing really exciting. You just make a power law mass function that goes up in time. But you can see that over here, the winds really prevent the formation of 10 to the 4 solar mass stars, right? So you cannot get beyond a few thousand solar masses just because the winds are just too strong, right? Of course, it's very simple, but I am quite excited about the possibility that this might have happened in a globular cluster. If you then plot at the M dots of both the accretion combined, right? So this is for all the stars in this mass bin, and the winds, you can see that the wind mass loss rate is completely dominated by the most massive objects in this IMF, right? So even though there are very few of these stars, right? There's actually a little peak here because of the more massive ones that they're not there now, they're being squashed into this region. But because it's an M squared relation of the M dot, it actually wins from the IMF slope, and it's completely dominated by the most massive stars. So then we have to do a bit of abracadabra hocus pocus. We have to get this gas into the low mass stars, right? And here we need more detailed models, right? But to proceed and actually make some quantitative predictions about what we can expect in a globular cluster, we say, you know, when these filaments come onto the star, it's not 100% efficient, right? You lose 50-ish% of this gas that comes out through a jet immediately. So it's not processed. It looks exactly like the gas in these filaments. So you build up some reservoir of material that's normal in abundances. And then when the first stars above 100 solar mass start appearing, they start to pollute this gas by these nitrogen enhanced, sodium enhanced material. But low mass star formation continues to happen in the usual way, right? So you get these half mixed stars at some point. Initially, you don't, because you don't have the massive stars yet. And then in time, you start to get more and more pollution in this cloud. So here, there are at least 10 questions you can ask me about exactly how that works. I'm happy to discuss that, but I'll just go straight do some quantitative comparison of this model to the data. So I show here the helium spreads in the clusters as observed, right? So the different points are different globular clusters, about 50 or so in the Milky Way for different iron abundances. And the lines are model predictions as a function of mass, right? So we find that we can keep the helium very low. Actually, we are a bit too low if you compare to the data, but we are on this sort of 1% helium, which is really good. And we also predict that there's a clear increase with cluster mass. And that's because more massive clusters start making massive stars earlier on in their formation process. So this mixture of gas starts occurring earlier. And for low mass clusters below, let's say, 30,000 in our model, there are no stars above 300 solar masses, so there's no pollution at all. So that explains why regular open clusters that we see in the Milky Way, they look totally normal. So the two challenges here, I think, are nicely addressed. Your challenge to challenge me on this. Right? I'm the car salesman here. I'm saying, hey, look, I solved this problem, but there are many things we can talk about, that details that one needs to test. But I'm going to proceed in that vein. But it's also nice now to look, because we have the IMF. We have the masses of the stars as a function of time. And that we can also do some quantitative predictions for the nucleosynthesis inside of these stars. So because the first prediction is just the average mass above some critical mass that has spewed those winds, right? So this here is the mass that was releasing the wind material, right? So because we trace the gas coming out of these stars, and we want to know what was the temperature at which the material was processed, right? So now we need to convert the masses of these stars to central temperatures. And if you plot stellar models, it's a surprisingly simple relation. I told you before, massive stars are very simple, as long as they're on the main sequence. So the mass of a star and the central temperature behave very simply. And this is true as long as helium is below, delta helium is below 0.1 or 0.2. So you can almost directly make this conversion from mass to temperature. And if you do that, I plot here now the central temperatures at which the winds were processed, or the material that is in the winds was processed. And you can see that it is in this interesting regime where magnesium depletion should be important, but not for all clusters, right? So low mass clusters, they were too cold to the stars to get to that magnesium depletion. And at higher masses, you start seeing it, and more so for the metal-poor stars. Now, and it's known that metal-poor stars are hotter in the center, but we don't use that. In our model, this is only because there are more massive stars. I've kind of normalized stars between 1,000 and 10,000 here. I hope everybody is still comfortable with that idea. I'm very comfortable now. But it's of course, we haven't seen them directly. So we should keep that in mind, that they are unicorns to some extent. But this addresses this third major challenge, is that there's a clear correlation in the abundance patterns, depending on the mass and the iron abundance of the globulus. So we thought about pushing this a little bit further. So if you have this mass temperature correlation, you can also look at nucleosynthesis results. So this is work by Nikos Prantzels and Corinne Charbonnel. They look at reaction rates in sort of fictitious stars, not actual stars, just at a constant temperature, a constant density. And they just put all the reaction rates that are relevant at these temperatures in, and then they look at how these abundances evolve. And you can see that apart from temperature, there's another parameter here, which is how far you enrich the star in helium. So there's some time parameter here. So for the nitrogen, sodium I showed you before, you can see that it's not so sensitive to helium. But if you look at aluminium and magnesium, these are very good thermometers, because almost nothing happens for magnesium up to this sort of 60-ish, 63 million Kelvin. And then suddenly magnesium plummets down, right? So the observed magnesium relative to other elements is a very powerful indicator of the temperature that the progenitor star, the polluters, had, right? Because if you would have a 75 million Kelvin star, so above 10 to the 4, you're depleting magnesium to the same level as oxygen, and that's really not observed. So the observations really favor to be somewhere in this regime. Some clusters don't have it, others have a tiny little bit. So now we are able to make these anti-correlations, right? We can say we average out all the winds that we get from the stars. We average the temperatures of all the stars in them. That gives us the endpoint of the anti-correlation, and then we dilute it with pristine gas to sit on this track, and we compare to the data. So for sodium, nitrogen, oxygen, sodium, oxygen, we're not too good. We're a little bit overshooting here. I'm not quite sure. So these data would like a little bit higher temperatures, more massive stars. But for magnesium, aluminium, we do really well. And I sorted these globulars in our model temperature, which you can see that this effect I just mentioned. So you have a tiny little bit of aluminium spread in low mass clusters that are metal rich. And then if you go to more massive clusters that are more metal poor, you start to get a much larger aluminium spread and a larger magnesium depletion, which is also what the data shows. So back to this figure, if you then say, okay, where are the stars that we need? Is, well, every star, even a 10 solar mass star, can create this anti-correlation, but it just doesn't come out of the star. So these stars are ruled out, right? Above 100 solar masses, you make the anticorrelation, and it also comes out. So that's a very good mass range to think about. And then you need to go above a few thousand solar masses to get this magnesium depletion. So the preferred mass range is somewhere in here, and that's what our models seem to suggest. So between 1 and 3,000 solar masses, right? Okay, one could stop here and say, okay, great, there were 1,000 solar mass stars, but it's really a bit frustrating that we haven't seen those stars. So we should test this idea and see if there's ways to test it. Now, as I said before, these stars above a few hundred solar masses are visible in helium-2, and now it starts to become an industry to find these lines. And I think one needs to go out and I say one because I don't think I can do that, but somebody would have to make stellar population models up to 1,000 or a few thousand and see if there's unique features that are different from 300 solar mass stars, right? So rotation could be very important here, but the metallicity as well. So at the moment, we can't say from this helium-2 line if this is 300 solar mass stars or 1,000 solar mass stars. The same is for this. This is for me also a little bit uncomfortable, and I actually learned a lot chatting to Mar about these abundance ratios and the different line diagnostics. But I'm sure next couple of years are going to be very exciting about that, especially because of JWST, right? So here you can see some of these high ionization transitions that require photons of high energy. And in the JWST community, people like to plot these sort of AGN predictions here in gray, and then stellar populations. So this is a metal poor stellar population. This is a metal rich population. And then they say, oh, I see this line, can't be a star, right? It must be an AGN. But you can see the effective metallicity is quite high, but if you add very massive stars, we get this line. We already know that, right? So this is a population truncated at 100 solar masses. So you can easily get to here by just allowing for 300 solar masses. So maybe we can also get this carbon-4 line if we allow for 500 solar masses or 1,000. Maybe we get to not nitrogen-4. I don't know. But I think this is interesting. So Mark made a very clear point this morning that she's only impressed above 100 EV when she thinks it's in. So I think that's very safe. But in the JWST community, people are arguing about these lines, and I think that's interesting to understand better. And then the final point I want to make before the pizza is that if there were stars above a few hundred or maybe 1,000 solar masses, this should create black holes that you wouldn't get otherwise, right? So I show here results from single star models for the black hole mass as a function of the ZAMS mass of stars for different metallicities. So for the globular clusters, you can safely kind of zoom in on blue and the purple. These are the metal 4 predictions. So there's a well-known gap here in stellar mass and in resulting black hole mass, which is due to pair instability, where the temperature and density are such that positron-electron pairs suddenly start to exist and create photons, and the pressure support disappears, and these stars just ripped apart, leaving behind nothing. So these models predict that you shouldn't see anything between 50 solar masses and about, well, the current models are 150 solar masses or 120. And people don't really care about that too much from the perspective of ordinary models, because you are really talking about 200 solar mass stars here. So people say, well, you know, is the bottom of the pair instability gap here or here? That we care about that for gravitational waves because we see 60 solar mass black holes. So are they second generation mergers, or is the pair instability gap wrong? Blah blah blah. But sorry, this should have appeared after that. And we in our model also should populate or have stars that create no black holes, but we should have tons of stars that create IMBHs above 100 solar masses, right? So that might lead to further gravitational wave in spirals, signals we may detect, but they may also still be there in globular clusters today. And it's an interesting mass range because there's solid evidence or lots of observational arguments against black holes above 10 to the 3, 10 to the 4, maybe 1 in omega Cen. But this mass range is extremely easy to hide in a globular cluster. So a 500 solar mass black hole in a globular cluster, I think we can go and look for it, but right now it's very hard to rule out that it's there. Yeah? So that's interesting. So we can do this both with gravitational waves, but also with local globular clusters and look for black holes in that mass range. So in light of the time, I think I just managed between 45 minutes. Yes, I'll leave you with the conclusion. So to summarize, I can give a lot of technical parts, but I think the model we have in mind is really one where multiple populations are a natural outcome if the gas densities are high, right? So it's not forbidden to make them in a young massive cluster, but it's much less likely to create those gas densities in a merging galaxy or star-forming galaxies at a residue of 0. So then the consequence is that the clusters must have had stars from 500 to 5,000. And even if you don't like the model, the nuclear synthesis is really telling us that already, right? So even if you say, well, all that star formation, I don't believe any of it, I would be very happy with that. But then I would say, but look at the detailed chemical abundances, and if the reaction rates are solid, if you believe that, then you kind of can only conclude that you need stars of around 1,000 solar masses to create those abundances. And so as a result, these black holes are probably formed, right? I think that's, I find that a fun connection between looking at magnesium, aluminium in the globular cluster and then saying, oh, there must have been 500 solar mass black hole. So there are some gravitational wave predictions. So we should see black holes above the parent stability gap, so above 100 solar masses. Currently, that's hard to see. The frequencies of the LVK detectors are a little bit too high. But there's other ways also to make these black holes by having repeated mergers. But the difference is that these repeated mergers should be high spinning black holes, and we can infer the spin from the gravitational wave signal. So maybe in the next observing run in a few years, otherwise with LISA, these black holes should be found. And yeah, there's a lot of interesting things to be done also by disentangling these extreme stars from AGN signals at JWST. So I'll leave it at that. Thank you.
Thank you for being perfectly in time and also for the very amazing presentation. So questions? Costa.
Hello, thank you very much. I have some binary questions. So we have this this coordination of the initial mass function. However, also the binary fraction in massive stars is high. From this modeling of the clouds, do you expect to have any binary massive stars like that, as we would expect from lower but high mass stars?
Yeah, that's a really good question. I've totally ignored that, mainly because I just don't really know. The models that we have should form the binaries, but we haven't pushed it to beyond 100 solar masses. So there are no numerical or hydrodynamical simulations sort of self-consistently forming stars in binaries. The one observational trend I find interesting is that it's true what you say that the binary fraction goes up with mass, but the binaries also tend to become tighter if you go to higher masses. So, you know, O stars could be in 3-day period binaries, right? So, and the most massive stars in R126 are single stars. So there are 5 stars that people have looked for with radial velocities, multiple epochs, and they seem all single stars. So whether the periods just shrinks if you go up in higher masses and then they just collide, or some other reason prevents them from being binaries, I don't know. But it might be that the binary fraction is actually really low. But honest answer is we just don't know.
And about thank you. And about the previous traditional models to explain these abundances, I see still that they are considering single star effects. However, now we know that there are other processes that affect the abundances, like chemical homogeneous evolution is very important.
Yes.
And can have even more dramatic effect than rotation, I guess, to bring these elements in the surface.
But it's due to rotation, right? This chemical. That is due to rotation, right? This homogeneous evolution.
Yes, but it's not like a models. In other models, they just consider some rotation and single stars. However, in chemical homogeneous evolution, you have an additional element that increases the rotation because you are in a binary.
Yeah.
We have more efficient mixing of the elements because of the effect of the binary. So
yes.
So it can create very different systems at metallicities, low metallicity, like we're discussing here. And also the stripping of the helium stripped star that I don't know if they're taking into account, but then it might have a strong UV emission like the one that we mentioned. But have they considered this, these newer models of binary stars, at least put some limits?
I think partially, yes. I know people like John Eldridge has been pushing this with BPAS, the stellar population or binary population models, by increasing both the mass, but also as much realistic binary physics as possible. So there are interesting features, and don't ask me the details, but I remember several of his presentations, even the high redshift community going to the edge of their chairs, like, what, you can make that line? I said, yeah, it's just a Wolf-Rayet feature that you don't get with single stars, but you get it with binary stars. So it's happening. It's going slowly, and there's obvious reasons, right? It's a parameter space. It really explodes when you include binaries, and then the physics becomes less certain. So, but yeah, rotation, even without binaries, right? So if stars, I mean, in our picture, they accrete very long, so they would be rotating also while they are already burning hydrogen. So this chemical homogeneous evolution is a necessary in our model. We have to have that. And you get it automatically at 1,000 solar masses just because the stars are fully convective, right? So even if they don't rotate, they are completely mixed. But then all of these things that people have predicted for 50 solar mass, these binary induced chemical homogeneous evolution applies here automatically. So you get bluer stars and much hotter. That's why I'm intrigued by this JWST lines. Like if your rotating star moves to the blue instead of to the red, and it becomes 100 kilokelvin instead of 5. That would change the spectrum completely. I just don't know exactly how yet, but I hope somebody's gonna add that into population models.
So, Nanda.
Thank you very much. Fantastic talk. I have a question. When you're speaking about all these very massive stars that were in globular cluster, right? Now, of course, observing black holes of intermediate mass are probably worse in globular clusters. There is a huge systematic and we're actually detecting.
Yes.
So we know there are many, but they are close to impossible to actually detect. However, pulsars, neutron stars are very easy to detect in globular clusters, so we know many of them, which would trace sort of a bit of the lower end of your mass range, right? Now, we don't see young pulsars in globular clusters. We don't.
No.
And there is no selection bias in this. It's way more difficult to detect the hundreds of millisecond recycle systems in globular cluster than detect a young pulsar. And there are plenty of very deep surveys. So my question is the lack of somehow a more younger population, let's say not the giga-year population of recyclables, the lack of them in globular clusters telling you something about actually the mass distribution of the lower end of the massive stars?
No, not really. I mean, at 12 gigayears, you shouldn't expect to see any young neutral stars anymore, right?
At the giga-year.
Yeah, no, so,
But when is your massive star population? When did it disappear?
oh, that's
in your models?
2 million years after formation, right? So it's really at the
Really?
right at formation. So it's they're all gone.
So now there would be all giga-year leftovers. That's what you're saying.
Yeah. And most of these, I mean, people have found these chemical peculiarities down to ages of 2 gigayears, but they're very weak. So the most obvious chemical anomalies are found at 12 gigayear clusters, 10 gigayear clusters. Sorry, I should have maybe made that point more clearly that there's a, yeah.
Thanks.
Other questions? Maybe I have one while they think. So you have mentioned that you form these stars also through accretion. I'm wondering, do you also produce a jet in this accretion process? And can this jet also contribute to the pollution of the other stars?
That's a good question. We assume that there will be a jet. It doesn't happen. I don't think there's any star formation models that self-consistently have the accretion disk and the jet forming, because there's magnetic fields involved in. You would have to resolve almost the star, right? So that's not really happening. Some people put the jets in by hand, but what we assume is that the material coming out of the jet, that there is material, but like about half of the mass that flows towards the star doesn't end up on the star, would be immediately released in the jet. And don't press me on why it's 50%. It's something that my star formation collaborators are very convinced about.
I'm an observer, I accept it.
And we assume that that material hasn't been processed yet.
Okay.
So it comes from the disk more than from the star.
Okay.
So, but yeah, we try to discuss a bit the picture of what happens when you have accretion and winds at the same time. So the winds cannot be spherical, right? Because if there's a enormous disk with a high accretion rate, the winds are forced to come out of the pole. And if the star is rotating, it must also be flattened. So then that also helps to make the winds come out to the pole. So if the jets are also coming through there, it sort of happens at the same time. So maybe, now I think about it, actually, the winds and the jets might mix while they come out. So maybe this mixing happens very close to the star already. But yeah, those are resolution problems we cannot really address in detail yet.
Okay, thanks. Question.
So these globular cluster intermediate mass black holes, where should you find them? Are these ones in this at the age of 12 years? Are they expected to be at the center because they dynamically move there?
Yeah, if they're still there, right? So the unfortunate thing is that they might not be there anymore because they would go to the center so quickly because they're so massive that the dynamical friction brings them there in a couple of million years. But then if there's more than one, they start interacting with each other, and there would be dynamical ejections of these intermediate mass black holes. So if they're not there, it doesn't immediately prove the model wrong, but there would be, it would be an important constraint on the model if we find that there's really absolutely zero evidence for black holes above 100 solar masses. In some cases, if they don't get ejected, so if there's a real mass gap between stellar mass black holes and intermediate mass black holes, which people argue, but the classic models say you shouldn't form any black holes between 45 and 150 solar masses. So if you have a big gap, if you have one very massive black hole remaining, or you start, let's say, with 100 intermediate mass black holes, they all get kicked out, then you're left with one or two. Right? So you have a binary intermediate mass black hole, or a binary with an intermediate mass black hole and a stellar mass black hole. In either case, if the binary is substantially more massive than the other black holes, it's very difficult to kick it out because the kick is just a momentum recoil. So if you have a recoil with a 10 solar mass black hole and a 1,000 solar mass binary, the binary moves very little. So that binary would stay there. It would just shrink with the interactions and then merge. And then it starts to get involved in the next mergers. And it could actually grow in IMBH like that. If there's no mass gap, if you just have a continuation in the black hole mass function, you start just throwing them all out, and incidentally, one might merge, but then it gets a relativistic kick, and then it's gone anyway. So only in the nuclear clusters, you could maybe keep one of those merger remnants, because the kicks are 500 kilometers a second or 300 kilometers a second.
Maybe let me ask, is there any question from online people? Just shout. I don't think so. And any other question from the room? We still have time maybe for one quick question. If not, so before we say bye, I just have two announcements. The first one, please wait for the speaker to come before devouring the pizza. And the second thing is that we are going to broadcast a talk this Monday, because the next Monday is the International Day of LGBTQ People in Science. There is a talk that we will broadcast in this room on Monday. We will send more details by email, but just take a look at that if you can. And by saying that, so thank you a lot.
You're welcome.
You downstairs for the